This video describes the design and fitting of the PC4 single vision corneal GP lens. My name is Randy Kojima. The PC4 was developed by the CAT Design Group, an international consortium of researchers, clinicians, and contact lens experts. It's distributed exclusively in Canada by Cardinal Contact Lens and Precision Technology. The first question we might ask when we fit single vision lenses is, why aren't GP lenses more comfortable? And part of the story is the movement, and that's seen in this case with the amount of movement that's evident with this contact lens. It seems vertically very unstable and moves a great deal, and the patient would therefore be very sensitive to all that movement. But GP lenses can be comfortable. We know in cases of adherence, when the GP lens is adhering to the eye, the patient feels it very, very little. They're actually generally quite happy with the comfort, even though we are not happy with a lens that adheres that isn't producing a good tear pump. But it tells us that when the lenses stop moving or move very little, the patients can't feel them. And Ortho-K is another example where these lenses are worn in the closed eye environment, and patients therefore don't feel them when the eye goes quiet. Another example is scleral lenses, these large diameter lenses that land so far out on the eye's surface, move very little, and therefore are extremely comfortable. So GPs can be comfortable, but what can we do to reduce their movement? That's the question. One of those answers is to use a larger diameter. Although this lens rides high and wouldn't be deemed an optimal outcome, we do have a lens that is extremely comfortable because it's not moving. So diameter helps. It helps to reduce the movement of the lens. When you fit a patient with a 9.5 diameter lens, it's more likely to move a great deal. Even if you have the right sagittal depth, we're not using all the depth of the eye to lock that lens into place. However, when you fit a larger diameter lens like an 11.0, you're using more sagittal depth, covering a broader surface of the eye, using a deeper lens that locks it onto center and can improve comfort a great deal. That's part of the story with the PC4, using larger diameter lenses. So the PC4 will use typically a 10.5 diameter lens, slightly larger for the bigger eyes, slightly smaller for the smaller eyes, but generally it's larger than your typical 9.5 lens. The PC4 standard diameter is 10.5 millimeters. That is to reduce the movement and again to increase the comfort. Another part of the PC4 story is how the lenses land. And let's take this example where we have a cornea that's relatively spherical. We have 0.2 diopters of central corneal astigmatism. Essentially, it's a spherical eye. However, is it spherical from the center to the periphery? And we look at the curvature in the middle, steepest. As we move away from center, the cornea gets flatter, more cooler contours, and that's seen on the topography itself, reddest in the center, bluest or cooler toward the periphery. This rate of corneal flattening is described as the eccentricity of the eye. Let's take another example. Here's a patient with the rule corneal astigmatism, approximately 1.5 diopters of corneal sill. But again, we see steepest in the center, flattest toward the periphery. So these eyes have a rate of corneal flattening. Although the center can be spherical, no eye is truly spherical from the center to the periphery. If it were possible to have a utterly spherical cornea from the center to the periphery, then the eye would be much deeper. But most eyes will flatten out as they move toward the periphery. Diseased eyes, keratoconic patients, might have much higher rates of corneal flattening. So the higher the rate of corneal flattening, the greater the change in the periphery of the lens that we may require. And that's seen here. This is a 10.5 diameter spherical optic zone lens modeled on a normal spherical cornea. And what we see is a healthy fit where the GP lens clears the corneal apex, but you'll notice this acute point of landing, this narrow or sharp area where the lens comes down and touches or aligns with the peripheral cornea. Again, this is using a spherical optic zone. Now let's put on the PC4 with its aspheric optic zone. Notice you have the same or very similar apical clearance. However, the lens has this beautiful landing in the periphery where it distributes its force over a broad area. And this may help to improve comfort because instead of landing over an acute point, we land over a broader area of contact. So when you compare a lens with a spherical optic zone or a high eccentricity like the PC4, you see this much better distribution of the pressure on the eye surface. So the PC4 employs a highly aspheric back surface optic zone to emulate the rate of flattening of the eye. Now, how do you fit the PC4? Well, let's go through step by step. The first step is to choose the lens diameter, and this is really quite simple. All we do is measure the visible iris diameter, subtract 1.3 millimeters, and that gives us the appropriate PC4 lens diameter. In this example, if we measure the VID as 11.8, subtract 1.3, that tells us we need a 10.5 diameter lens. Step number 2 is choose the base curve, and this is fit 1.5 diopters steeper than the flat K reading. Now, why so much steeper than the flat K? And the reason is you have a very high eccentricity back surface of the lens, which is meant to emulate the rate of flattening of the cornea. So the base curve needs to be much steeper at the center to create the apical clearance that we desire. If you were to choose a PC4 with a base curve on flat K, we can see in this model how the lens would hit the corneal apex with excessive edge lift, most likely all the way around. So a lens built on flat K is most likely to be too flat for the cornea and would be hitting the corneal apex. If we were to fit a base curve 0.75 diopters steeper than flat K, we may end up with a tiny apical clearance, but without the appropriate landing in the mid-periphery, most likely a flat fit with excessive edge lift. If we fit the lens 1.5 diopters steeper, that's the optimal point that we want to begin with. That gives us the apical clearance that we desire with landing in the mid-periphery to create that stable fit that we desire. If we were to go much steeper, 2.25 diopters steeper than flat K, now we would still land in the mid-periphery, but the edge might be a little too tight and we're most likely to have excessive apical clearance. Let's take an example. Here we have a normal cornea, relatively spherical in shape, a good candidate for a corneal GP if soft lenses had not been successful for this wearer, or if there was some concern about the health of the eye. The most healthy contact lens on the planet would be a corneal GP worn in day wear. Now, we place a lens on eye inappropriately flat with a base curve on flat K. We see that lens hitting the corneal apex and decentering off. So this is clearly a lens too flat for the cornea, and we should therefore be steeper. What if we were to fit 0.75 diopters steeper than flat K, still a little bit on the flat side, we notice the lens wanting to ride a little bit high and lagging down slowly. So this lens, again, may still be on the flat side. It's not centering as well, but acceptable. Let's go 1.5 diopters steeper than flat K. Now we have a lens that clears the corneal apex beautifully, lands in the mid-periphery, wants to be relatively stable. We have the optimal PC4 fitting. What if we were to go 2.25 diopters steeper than flat K? Now we have a great deal of apical clearance, creating some bubbles in the center, some dimple veiling from that excessive apical clearance. The lens wants to ride a little on the low side, so clearly we are too steep for this eye now. Now, in terms of edge lift, the first thing that we want to know is, do we have the right apical clearance but an inappropriate edge lift? Or is the eccentricity of the lens or depth off? And in this case, we can see the lens clears the corneal apex, so the sagittal depth looks acceptable, but the edge lift might be a little thin in some places. What we're looking for is a 0.5 millimeter width of edge lift, 0.5 millimeters width of edge lift. In this case, we see an edge lift looking more like a millimeter, much wider than we desire, although the apical clearance looks acceptable. So this is important information for your consultant to know. Do we need to change the sagittal depth of the lens as well as the edge lift, or is it really only the edge lift that needs to be altered? Step number 5 in fitting your lens is choosing the appropriate lens power. Now, if you're using the diagnostic set, of course it's simple. We take the lens power plus the vertex over refraction to give us the final lens power. So if our trial lens is -5, over refraction -75, we simply order a -575. If we're calculating the lens empirically and not using a trial set, then we would take our vertex spectacle Rx, or vertex when necessary, adding 1.5 diopters for the steep add minus compensation, the fact our base curve should be 1.5 diopters steeper than flat K. Then if we have an Rx of -450, vertex to 4.25, add your 1.5 diopter lacrimal lens, that gives you a 575 final lens power. So the PC4 is a next generation of GP lens. It does not employ conventional 9.2 or 9.5 diameter lenses, and it doesn't employ conventional optics, conventional spherical central optical zones. It uses a larger diameter and a high aspheric to reduce movement, to improve the alignment with the peripheral cornea, and then to provide that GP lens vision that we expect to be exceptional. This platform of using the larger diameter and the asphericity on the back surface is not just for single vision. It can be applied to multifocal lenses for presbyopes or multifocal lenses for adolescents in myopia controlling GP lenses. So the PC4 is used as the back surface platform of the Apex multifocal lens. Again, that can be used both in presbyopia and in myopia control in kids. For more information about the exciting PC4 design, contact your customer service representative, consultant, or sales representative from Cardinal Contact Lens or Precision Technology.